In the previous video, we started to write the functions for solving the MNIST problem using a neural network with two hidden layers. So we finished writing the function for defining a single layer, which is named layer here, and the function for constructing the network, which is named inference here. So in our current implementation, we're actually using the same number of neurons for every hidden layer. For a more complicated problem, we may want to use different number of neurons at different layers. And the inference function will compute the model predicted logits, the logits predicted using our neural network for any input image. So it encapsulates all the calls. It encapsulates all the calls to the layer function. And once we have the predicted output logits, we can compare them with the ground truth labels and compute the loss, or compute a quantification of the mismatch. It's usually called loss, which is basically just a number to indicate the kind of mismatch between the prediction and the ground truth. Right. So now let's write a function to quantify the loss. So def loss y logits. The loss function is going to expect two inputs. So the ground truth label y, and the model predicted, or the logits predicted using our neural network, and it should return a measure of the mismatch, a number that quantifies the kind of mismatch between the prediction and the ground truth. So in our single layer implementation for the logistic regression problem, we were manually computing the cross entropy, right? We're manually computing the cross entropy by doing a dot product between this kind of a one hot encoded ground truth label and the logged prediction, right? Natural logged. And then we were basically just using the exact mathematical expression for computing the cross entropy. Right, that's the solution that we. How we actually computed the cross entropy in our previous one layer logistic regression solution. Right. And here we are going to compute the cross entropy using a function that's provided by TensorFlow. Let's call it cross entropy equals to tf.an.sparse softmax cross entropy with logits, and then it's going to expect two inputs: the labels, which are the ground truth, equals to y, and then logits equals to logits, right? So both inputs must be the keyword arguments, right? You must use the keywords, labels, and logits, and then here we just directly passing the inputs y and the logits to this cross entropy with logit function. And this function is going to compute the cross entropy based on the logits of the output layer. So it does not really require us to sort of normalize the logits first, right? Because for the output layer, which is actually a softmax layer, right? In order to actually get the neuron output y, from the logit z, you have to go through take the exponential of the logits, right? You have to take the exponential of the logits and then normalize the exponential of the logits through all output neurons, right? So that process that entire process of converting the logits to the neural outputs, converting the z's from the to the y's, is called a softmax activation function, right? So this softmax cross entropy with logits, sparse softmax cross entropy with logits. This function is going to take the logits directly. So it doesn't. So you don't want to sort of, you don't need to normalize or do the exponential thing. You don't need to actually use the softmax activation function before you actually pass in the logits, right? So that's one of the nice things about this particular function. And the ground truth that's passed to the labels keyword argument are the ground truth labels that are not one-hot encoded. So you cannot actually pass a one-hot encoded label to this particular keyword argument, right? It's actually expecting a label that's not one-hot encoded. So when we actually did when we loaded the data in the previous video, right? When we loaded the MNIST dataset using this read datasets function at the beginning, we set the keyword argument one hot to false, right? We set the one hot to false, and the reason for this particular choice in the one hot input arguments is just because of that, because of this cross entropy with logits function expects labels that are not one hot encoded, right? So here we actually set the one hot to false. Right. So once we have the cross entropy, then we can compute the loss using the reduce mean function, and this part is actually identical to the logistic regression case, right? Here we also use the reduce mean on the x entropy to get the loss, right? So here we're going to do the same thing, but we're going to assign the output to cost, right? Tf dot reduce mean, and then x entropy. Let's give a name this time. Let's call it loss, right? And then we can just return the cost, and that's our loss function. That's our loss function. And this step is identical to how we computed how we quantified the mismatch between prediction and the ground truth in the linear logistic regression, or in the logistic regression case. Right. And then once we have defined the loss function, we can write the function for defining the training operation, right? So def training, and then the input is supposed to be cost, right? So if it takes only one input, right, which is actually the cost or the loss, depending upon how we call it, right? The value that's returned by the loss function is the tensor that's returned by the loss function is the cost. It's called cost, right? But it doesn't have to be called cost. You can sort of call it any name, right? But it's just a quantification of the mismatch between prediction and the ground truth, right? And we will still use the gradient descent optimizer. So our optimizer is going to equal to tf.train dot gradient descent optimizer, and then the input is supposed to be the learning rate. Right. And the learning rate is actually a hyperparameter, which we have defined as a Python global variable at the beginning of this particular file. Right. Here we just pass this global variable to the optimizer, and then we can just training up equals to optimizer dot minimize, and then we pass the cost to it, and then we can just return training up. Right. here we just pass the input cost directly to the optimizer's minimize method, right? And then return the training op. And this function is actually identical to how we obtain the training operation in the logistic regression case, right? So optimizer equals to the gradient descent optimizer with the learning rate passed in as the input, and then calling the minimize function of the optimizer and pass the loss, right? And then we get the training op. Here this function, we're just inside of this particular function, we're just encapsulating these two steps into like a one function call. And the last function we are going to write is the function for evaluating the model, either by using the validation dataset or by using the test dataset. Right. So let's def evaluation. Evaluate. Let's call it evaluate. Like y logic. Y logics. Not logic. Logics. It's plural. So the input y is again the ground truth labels, either in the validation dataset or in the test dataset, right? And then the logits are the logits predicted using our neural network. And for evaluation purposes, we don't really need to compute the cross entropy, right? We're not gonna sort of compute the gradients using that loss function, right? So we don't really need to sort of compute the cross entropy and then compute the cost, right? We can do a simpler thing. We can do a simpler thing here for just to get the performance value, right? And all we need to know is actually the accuracy of the prediction, right? So how do we actually get the accuracy, right? So for each test or validation example, we're going to determine if the neural network's prediction is correct by checking whether or not the highest logit corresponds to the target class, right? In our case, the target class is basically the label, right? What the label is actually telling us. So for this kind of purpose, we can just use the TensorFlow's in top k function. So let's define correct equals to tf.n.in top k, and then logits y1, right? So this in top k is gonna allow us to determine if the neural network's prediction is correct by checking whether or not the highest logit, because here it's 1, right? That's the highest logit. If you give it like 2, then it's gonna look into the top 2 logits, right? That kind of thing. So here it's gonna just look at the highest logit and see if it actually corresponds to the target class. And this is gonna return a one-dimensional tensor. This function is gonna return a one-dimensional tensor that's gonna be filled up with Boolean values, true or false, right? So we need to cast these Boolean values to floats and then compute the average. And this is going to give us the accuracy. Again, we're going to use reduce mean, and then tf.cast. We're going to do a cast, right? Cast correct to tf.float 32, right? And then just to return the accuracy. So if you look at, we also had these two steps when we were solving the solving the logistic regression problem, right? But we're sort of comparing the top logits with the we're doing that by hand basically, right? So if you look at so correct prediction equals to tf.equal tf.argmax y predict y 1 tf argmax y. So doing this kind of a comparison, comparing the index of the largest logit not exactly the largest logit. It's actually we have applied the softmax function on the. We actually have applied the softmax function on the logits to actually get the y predict, right? So y predict actually equals to the softmax function applied on the logits here, right? So it's not exactly the same, but in principle they should give you exactly identical results. So if you want to sort of keep using this particular line to evaluate how to check the mismatches or check the accuracy, then you will have to sort of convert the logits into the neuron outputs by using the softmax activation function, right? And then the reduced mean is sort of this line is identical actually. So to go from the correct Boolean vector, Boolean tensor to the accuracy, right? This step is actually identical. So if you compare this line with this line we're writing here, that's exactly the same, almost the same actually, almost the same. Maybe except the name of the correct is kind of different. Right. And in top K is going to allow you to use logits directly, so you can avoid doing this kind of conversion by calling the softmax activation function. Right. So, and now we have finished writing all the functions needed in order to actually construct the neural network and build the computational graph. So if we would like to actually reuse these functions when constructing other neural networks, we can try to make this function, make this entire file that I have been writing so far, into a Python module, and later on we can just import that module when we're solving other kinds of problems, right? And in order to do that, we need to sort of put our following code into a conditional, and this conditional is going to look like that. If so, double underscore, this is double underscore name, and then double underscore again. We're comparing name to double underscore main, double underscore, right? So this conditional means that all the codes that's gonna follow in this particular line will be executed only when this entire file is being executed as a script, right? So we're comparing this name with main, which means what? Which means we're trying to execute this entire file as the main function, basically, right? So the reason for doing that is that if we just write the codes for constructing the graph and then executing the graph, that kind of thing, without this line, if we just do that without this line, then afterwards, if we try to reuse those codes as a module, when we try to import this particular module into other scripts, then all the codes in the following will be executed when we are importing that particular module, this particular module, this module. And that's not exactly the behavior that we want, right? We don't want to sort of to solve the MNIST problem every time we import this particular file into another script. We don't want to do that, right? And this conditional is going to check that if we're actually importing this particular file into another script or something, then it's not gonna execute all the lines that's following. Right? It's not gonna try to solve the MNIST problem. Right? So if we are importing this file as a module inside of another script, the codes that I'm gonna type now, starting from now, all the codes that I'm gonna start typing now are not gonna be executed. Right? And now let's try to write the code to build the graph using those functions that we have written so far. And we first define the dimensions. So n inputs is gonna equal to 784, and then n hidden. Let's just give like 256 there. So n input is the total number of features, and n hidden is the total number of neurons inside each hidden layer. We first reset. We need first we're gonna do a reset of the default graph. And then, and now we can sort of define the two placeholders for the input image data and the corresponding ground truth labels. So x is going to equal to tf dot placeholder. Right. It's going to be a float 32, right? And then shape is going to equal to none, and then n inputs, and name is going to equal to x, and then y is going to equal to tf dot placeholder, right? Tf dot int 64, right? And then shape equal to not any shape, and name equal to y. So even though we have specified none as the only input here, but because we have only one none here, so it means that the shape is still going to be one-dimensional, right? So the shape is going to be one-dimensional just because we have one none here, right? And the number of elements in this one-dimensional tensor is can be any because it's a none here, right? Can be any. And then we can obtain the predicted logits by just calling the inference function, right? So x and then n hidden, right? And here we are calling the predicted logits output, right? But the output actually is going to hold the predicted logits predicted by using our the neural network with the two hidden layers. And now the cost that quantifies the mismatch between the prediction and the ground truth can be obtained by just calling the loss function now. So cost is going to equal to loss y output, right? We assign the output tensor to cost. We assign this the output from the return value from the loss function to cost, right? And then we can use this cost as the input to the training function. Let's just call it train op equals to training cost, right? And now we have a training operation, and we also need an evaluation operation, right? And the evaluation operation can be obtained just by calling the evaluate function, and then passing y and also the output, right? That's the model prediction. And now we can execute the graph now. But if we would like to actually convert this file into a Python module later on, we actually need to move the line for loading the MNIST data into this conditional also, right? Into this particular into this conditional, right? Because we don't want to sort of load the MNIST data every time we import this particular file, right? So let's just move this line to down here. This line is going to load the data. So build the graph. Load the MNIST data set. And now we can execute the graph. And then we need to open an active session. Right. And the first thing we're going to do is to actually initialize all the variables. So this is one step that we cannot sort of forget. Global variables initializer, so function, and then here we and now we can write the loops over the training epochs and also the training batches. And this part of the code is actually identical to our linear logistic regression program. So I'm just gonna sort of copy it over. the indentation is like wrong. Right. So that's the loop over the training epochs. Right? Training epochs is one of those hyperparameters. Training epochs. We have set it to like 40, and then the total number of batches for each of the epoch is going to be maybe let's try the different way. Let's by using a double slash to do an integer division. So in Python 3, it's kind of double slash is going to do an integer division. If you just give it like a 1 slash, it's going to do a floating point division. It's going to, even though these two numbers are actually integers, it's not going to do integer division. The output is going to be automatically floating point. Right? So if we want an integer division, we have to use double slash in Python 3. So the total number of batches is just going to be the total number of training examples divided by the batch size. Batch size is another sort of global parameter, hyperparameter. Batch size equals to 50, right? So this way we get the number of batches, and then the batch index is going to range through the total number of batches, right? And we need to feed the data for a mini batch by calling the next batch function, right? And provide, and this function is provided by the MNIST train inside of this particular object. And then we can just run the training operation and feed in the data that for the mini batch. Right? And after each epoch, we just use the validation dataset to evaluate our model. And again, this part is kind of identical to the linear logistic regression case. Right? So I'll just copy it over. We do the validation after every epoch, right? So, if I want to show the entire line, it's gonna maybe a better way of writing this piece of code is just define val feed dict then equal to x right, and then y equals, and then we can just feed dict, replace this line with val feed dict, right? The validation error is just the one subtractive validation accuracy, basically. Right? Oh, I see. So the accuracy is not. What I should do is to not use accuracy. There's no accuracy here. It's called eval op, right? It's actually run the evaluation operation, and then give the feed dict to the val feed dict to the feed dict, and then that's gonna allow us to print out the validation. Right. So sure about the indentation for this one. So what I'm gonna do is I'm gonna reduce one more line. Format like that, and then after all the epochs are done, I can just we can evaluate the model using the test dataset now, right? So let's do a print training finished, and then we can just do a test feed dict is going to equal to x and then ist dot test dot images, right? And then y and then ist dot test dot bl labels, and then again we can do a test accuracy or let's just call it accuracy, doesn't really matter. Accuracy just gonna equal to sys dot run, again eval op, but with the feed dict set to test dict, right? Test feed dict. Right. And then we can just print test accuracy. Right, accuracy. And now we have finished writing all the codes, right? Both for constructing the graph and also executing the graph. Now let's give it a run and see if we made any mistakes. Looks like I have made some mistakes. No module named TensorFlow.example. TensorFlow example. Did I type it wrong? Or examples, not example. So tutorials, examples, and then tutorials, and then MNIST. Okay, so that's one of the mistakes I made. And you can see that the validation error is actually reducing after every epoch. So started with like 0.08 or something, and then now it's close to 0.05. So it should reduce to about 0.02 or around 0.02 something, right? In fact, this particular layer function that we have written here, right? If you don't want to write the layer function by yourself, TensorFlow actually provides a function that's sort of very, very similar to the layer function that we have written by ourselves, and that function is called dens, I think. Right? It's got a different it's got a function for and how do we actually use the dens function is pretty much the same as how we actually use this particular layer function. In fact, TensorFlow actually has so you can sort of Google TensorFlow layers dens, right? And then you'll be able to find the definition for the dens function, right? And then the dens function is going to require the input, the neurons, the number of neurons for the layer that you are defining, and then it's going to require a name, a keyword argument name, right? It basically tries to set up some kind of name scope or variable scope inside of that function using the name keyword argument that you passed in, and then it's also going to require, not exactly require, but it also has a keyword argument called activation, right? And you can pass a ReLU function or a softmax function, that kind of activation functions into that TensorFlow's dens function to construct the layer, right? And maybe in the next video I can demonstrate how to use the dens function to construct the layer, right, without using this particular layer function that you have defined by yourself. Again, there's a high level, very high level TensorFlow APIs that allows you to actually construct this kind of a neural network by using less than 10 lines of code. Right? But by going through this particular example, we can see that we have a better understanding about the neural network in general and how TensorFlow actually organize things together. And we can actually so the functions that we have written so far, you can actually use it to solve other problems just by changing a few parameters, right? And because it's written by yourself, you have a better understanding or better grasp about what's exactly happening, right? And if you want to sort of configure the architecture of the neural network, you have lots of freedom to do that, right? You can tweak, for example, the number of hidden layers. You can tweak the number of neurons inside each hidden layer, that kind of parameters. It's actually very easy to do, and as you can see, all it involves is just by changing some of the parameters, input parameters to some of the functions that we have written so far. And but one of the drawbacks in this kind of in solving the MNIST problem is that we are just using every pixel, this kind of flattened out pixel, as the kind of feature, right? By doing that, by doing this kind of flattening process, we're actually losing information about the relation between neighboring pixels, basically, right? So maybe by flattening it is not really a very good way for defining the feature, right? So now the training process has finished, and the test accuracy is about 97.59%, close to 98%. Right? So if we actually put in more hidden neurons, maybe it can exceed 98% of accuracy. But this has been a quite interesting exercise. I myself have learned a lot by going through this particular exercise. This MNIST example is extremely useful as a tool for understanding how those neural network actually works, right? And in future videos, we're going to do something that's slightly more complicated, right? We're going to look at the convolutional neural networks and those recursive neural networks and autoencoders. Right? Those are typical neural networks that has been used quite widely and has provided very good performance.